Hello, welcome to another module of this course, analog circuits. In the past module we had covered about the high frequency response and also given a circuit how to find the upper and lower 3 dB cutoff frequencies. Now in this module we are going to take up an example, because all the concepts that we introduced in the last modules, it may be a little difficult to understand in the absence of an example. So let us consider an example. However, before going on to an example, I will just introduce a concept called the Miller's theorem, which is an important tool used for determining the frequency response of many circuits. Suppose you are given a circuit like this, a series element with admittance y, where suppose at the input the voltage is V1 and I1, at the output the current is I2, voltage is V2 given equal to kV1. Then it can be shown that this whole circuit can be reduced to this form. Where this y1 is given by y times 1 minus k and y2 is given by y times 1 minus 1 upon k. So, we are given a circuit like this, admittance, a series element having admittance y and output voltage V2, which is k times the value of the input voltage V1. Then that circuit can be reduced to this. The proof is fairly simple. The proof is somewhat like this. So, for the first circuit, the current I1 is given by V2. So, I am here is given like this, which in turn is like this, which in turn can be written as okay. Now let y1 be equal to I1 upon V1. Then from this equation, where I1 upon V1 is given by y multiplied by 1 minus k, then I should be able to write y1 is equal to y multiplied by 1 minus k. Similarly, I2 is given by y V2 minus V1, which in turn is equal to y. If I take V2 out, then this is V1 upon V2, which is equal to y V2 1 minus 1 upon k. So, here also what we see that if we have y2 given by I2 upon V2, then that y2 is equal to y into 1 minus 1 upon k. The input you will have an admittance whose value is given like this y1, and in the output you will have another admittance y2 whose value is given like this. That is the proof. Now, we will come to the application of this theorem in a moment, but first let us go back to the example I was mentioning. So, suppose you have a circuit like this, this is the equivalent linear model of a device called a MOSFET. Now, first thing that you note is that there is no DC blocking capacitor, and that is why omega L is not present, only omega H is present, because I mentioned that omega L is present for those circuits that have an input blocking capacitor. So, if you would have a capacitor like this here, then you would have an omega L. Since that is not present, hence this does not have an omega L. So, then what is the, so okay, so now that it only omega H is present, what is the mid band gain or what is the DC gain? So, for calculating the DC gain, what you do is you open all the capacitors as if the capacitors are not present, and then find out VO upon VI. So, in the absence of any capacitor, VGS, this voltage is given by VI times R in upon R plus R in. VO is given by minus GM VGS RL, which is equal to minus GM RL R in upon R plus R in VI, from which VO upon VI is equal to minus, this is R in GM RL R in upon R plus R in. Okay, so, this is the DC gain or the mid band gain. Now, RGS or okay, now since we have to find out only omega H, we know that omega H is given by sigma RIO. So, this in turn we can write for this particular circuit CGS RGS plus CGD RGD, since we have only two capacitors present. So, therefore, how to find out the values of this RGS and RGD? Let me go back to the circuit once again. So, for finding out RGS, as I said, what you do is you open this capacitor. I think it is not visible. Yeah. So, for finding out RGS, you open this capacitor CGD and then find the equivalent resistance across these two terminals. If you open this capacitor, then this capacitor is disconnected, is basically this part of the circuit is disconnected from this part of the circuit. So, in that case RGS will simply be equal to R parallel to R in. Of course, here another point is this VI has to be shorted, the all voltage sources should be shorted and all current sources should be opened. Okay. Now, what about RGD? So, to find out RGD, what we do is we open CGS and then find out what is the equivalent resistance across the CGD terminals. So, to do that, let us try to solve it, this VGS. Okay. In order to find this VGS, suppose the current flowing is Ix. So, VGS is equal to minus Ix suppose the current is flowing in this direction, sorry. VGS is equal to minus Ix R parallel to R in. Okay. Ix, this current, is equal to GM VGS plus VGS plus Vx. So, here what we are assuming is that this is open, there is Ix here and the difference between the two voltage is equal to, so this is plus, this is minus, this is Vx, okay, upon RL. So, this current Ix is equal to this current flowing through this dependent current source and the current flowing through this RL, which is, so the current flowing through this RL is the voltage at this point divided by RL, and the voltage at this point is Vx, which is the voltage across the capacitor terminals, plus the voltage across the CGS terminal, that is from this point to ground. So, now solving this, so if we substitute in place of VGS this formula, what we get is minus GM Ix R parallel to R in plus 1 upon RL times Vx minus Ix. So, this Vx comes here and VGS is simply Ix multiplied by the parallel combination. So, this voltage VGS, the voltage at this point is Ix, the negative of Ix multiplied by the parallel combination of R and R in. Okay. Upon 1. Okay. So, solving this, what we get is and this is equal to our R G D, isn't it? V x upon I x is the equivalent, is equal to the equivalent resistance across C G D with C G S opened and all voltage sources shorted, all current sources opened, all independent, not the dependent current sources. So, then this R G D comes out to be, if we simplify the previous expression a bit, okay. Now, this upper 3 dB frequency is, as I was mentioning earlier, is equal to C G D R G D plus C G S R G S. So, now we have the value for R G D, we also have the value for R G S, we know the values of C G S, C G D, substituting them we can get the value of omega h. Now, let us try another method, which is using the Miller's theorem. So, once again we will draw the circuit. If you find out the DC gain V 0 upon V I, so our V I, of course, V I dash, let me say, V I dash is of course at this point. So, this V 0 upon V I dash for DC comes out to minus G M R L, and which is equal to the value of K. So, then now doing the Miller decomposition, that is, if we just like while discussing the Miller's theorem, we had split our circuit in this form, recall, where this Y is now split into two admittances Y 1 and Y 2. Now, one thing I would like to mention for this Miller's theorem is that this theorem is valid only when the input and output conditions are kept the same. That is, the V 1 and I 1 and V 2 and I 2 are the same for both cases, only the internal structure is changed. So, if that is the case, then it is not a good method for finding out the output impedance, because when you are trying to find out the output impedance, you short all your sources. But then for Miller's theorem to be valid, no change in the input and output source voltages and currents can be done. Hence, output impedance cannot be measured using this theorem. However, input impedance, if we want to find out the input impedance, then this is a good method, because while finding out input impedance, you do not make any changes in the output or input. That is, you do not have to short or open the output or short or open the input. Therefore, Miller's theorem is only valid for finding characteristics at the input port, not so much at the output port. With this in mind, the input part, that is the y1 part of this circuit, the equivalent y1 part becomes something like this. So, here the CGD is that y part, that is now split into two parts, and the one which appears at the input will be 1 minus k. So, here k is minus GMRL. So, this will be 1 plus GMRL. So, then if this is my equivalent input circuit, then the input, the value of omega h or the dominant pole is very simply written as the input total capacitance multiplied the input total resistance. Now, what is this CT? Now, looking at this circuit, can we write CT, if we go back to this circuit, can I write CT as simply the parallel combination of this CGS and CGD times 1 plus GMRD is equal to CGS plus CGD 1 plus GMRD, and R equivalent is the parallel combination of R and Rn. Therefore, my omega h is simply equal to 1 upon CT R equivalent. I would just like to make a correction in this formula. Omega h is 1 upon CT R equivalent, and similarly for the previous case also, I think the formula which I gave for this omega h in this case while discussing the previous method, the formula that I gave was this will be 1 upon Ci Ri 0. Please make this correction. Okay. There was a slight error. Omega h is equal to 1 upon sigma Ci Ri 0. Sorry for that. And here also omega h will be equal to 1 upon CT R equivalent. Okay. And finally, the best way to find out the value of omega h is to do a rigorous solution of the, using traditional Kirchhoff's current and voltage laws. We can rigorously find out the VO upon VI formula. So, the third method will be the rigorous derivation. And if we do that, what we will find is that this omega h, so here we are not using any Miller's theorem or any using those dominant pole derivation techniques that I discussed earlier. Here we are simply doing a V0 upon Vi, and based on the value of this V0 and Vi, we can find out what those dominant poles are. So, if we do that, this value of this V0 upon Vi comes out to be this. So, first thing you see that the denominator is a polynomial of second order, therefore, we will have two poles, the first pole being and the second pole. If you solve this polynomial, it will be given like this. Usually this GMRL is a somewhat is a quite a high value, therefore, all the other terms will be negligible, this CGS and CGD terms will be negligible compared to this middle term, and this usually reduces to GM upon CGS, which is also pretty high. So, the definition of dominant pole where omega p2 should be much higher than omega p1, so that omega p1 becomes the dominant pole is valid here. And what we see is that this omega p1 is exactly equal to the first method, to that value of omega h that we derived using the first method, and nearly equal to the value we derived using Miller's theorem. Hence, the method, that is by substituting capacitances with opening up the capacitances and then finding out the equivalent resistance, is a valid method, and it is proof that the method is applicable for finding out the dominant poles of a given analog circuit. Also to note that the Miller's theorem is also somewhat convenient, it appears to be a little easier than the other method in finding out the dominant poles. And of course, the final proof that there is a dominant pole, what is its value, or whether it is indeed the dominant pole or not, is by a rigorous method which we showed just now. That is the best method, but the other methods are also equally applicable. So, with this we come to an end to this module. In the next module, we shall be covering the topic of feedback. Thank you.